What's up, gamers? So, we need to take notes today, but I'm not here. I'm at a funeral, and I can't really give you any assignments without these notes, so we're just gonna have to do them like this, and I'm sorry, but that's just kind of how it is sometimes. Also, this is what my face looks like without a mask on. So, today we are taking notes over the properties of water, and it's going to kind of explain a lot of the stuff that we did in the lab yesterday, so I'm going to make my face smaller. Goodbye, me. And let's take some notes. So, when we left off a couple of days ago taking notes, we were talking about molecules, okay? And I want to talk about the molecules that have to be present to build a living organism, okay? We're going to call them the molecules for life. That's what this is up here, okay? And there are 5 molecules for life, like things that you have to build a living organism, okay? So our first one is water. Okay, and that's what we're talking about in this unit, and that's what we did our lab on, yesterday, is water. Our second molecule that we need to build a living organism is a carbohydrate, okay, or a carb, like carbs, like in bread, okay. Our third molecule is a lipid, which is the fancy word for a fat, okay. Then we have a nucleic acid, which is the fancy way to talk about DNA. And then finally, we have proteins, okay? Those are the 5 molecules that you have to have, you put them in a bowl and mix them all together, a living organism comes out the other side. This chapter, we are focusing on water. Next chapter, we will talk about the other 4. But right now, we're talking about water. And then there we go. So let's get into it. Water's a big deal on our planet. We talked the other day about how, if you are going to go to a new planet to look for life, the first thing you look for is water. Okay, so on average, water makes up between 70 to 90% of all organisms on Earth. 70% of all organisms is water. Okay, I think in humans it's like 73 to 78-ish. And the reason that this is a range is because, you would expect a jellyfish to have a lot more water in its body than a human would. Another cool thing about water, and we don't really think about it that much, but water exists in all 3 states on our planet. On our planet. So what that means is that water is a solid, a liquid, and a gas, all on Earth. Now, we take this for granted. We don't really acknowledge how cool that is, but think about when the last time that you saw liquid oxygen was, okay? So it's weird that our planet has all 3 stages of water just chilling out on the ground, okay? So, 72% right there. I'm so smart. You can see that right there. 72% of our body is made of water, okay? So let's talk about why water is so interesting and why water usually equals life. Okay, so the major reason that water allows living creatures to exist is water is a polar molecule. Okay, now what does polar mean? Well, polar means that so think about the Earth. You have the poles, so the North and South Pole. Polar just means that there's a this side and a that side. So there is no, let's say, distinct symmetry. Okay? If you cut it down the center, the sides are not going to be the same. Okay? So what that means specifically for water is that here's a water molecule. Water is H2O, and I would probably draw this in your notes because we're going to come back to this molecule a lot. But here's H2O. It's got 2 H's and an O. H, or hydrogen, is a very tiny molecule, or a very tiny atom, Oxygen's a very large atom. Now, because oxygen is larger, that means that it loves electrons. Okay? Now this is a molecule, which means that it's held together with a covalent bond, so they are sharing their electrons. But because this oxygen is really big and really powerful, he's going to be holding those electrons to his body closer. Okay? So what that means is that overall, the molecule stays together, but because electrons have a negative charge and they are sitting closer to the oxygen has a little bit of a negative charge itself. Okay? So the whole molecule kind of works like a magnet, where one side of the molecule is a little bit negative and then the other side is a little bit positive. Okay? Now what that means for us is that water is really good at making hydrogen bonds. And that right there is what is going to give water all of the special properties that allow life to exist on our planet. Okay? Now we saw this in our experiment yesterday where we poured oil in the water and it did this business. Let me tell you the reason why. So water is polar, which means that it has a positive side and a negative side. Okay? Oil is non-polar. Okay? Which means that all sides of the molecule are identical. And what that means for us functionally is that polar and non-polar molecules do not mix. Okay? That's why the oil bubbled up and stayed away. Polar and non-polar molecules do not mix. Okay? You cannot get them to mix with each other. That's why the oil did this. Okay? So, yes, hydrogen bonds. So here we have some water molecules, okay? The oxygen side's a little bit negative, the hydrogen side's a little bit positive, and they're just going to kind of move around and, live their best little life. And as they are moving, when they come into contact or get near another water molecule, what they're going to do is they're going to hydrogen bond right there, which is that slight, like, hey, how you doing, attraction between two different molecules. Now, one hydrogen bond is not that impressive, okay? But when you get lots of hydrogen bonds between lots of different little molecules, that is exciting, okay? And that is what gives water all of its cool properties, is those hydrogen bonds, okay? So the first property of water, which is what this says behind my pictures, the first property of water, move that down, is cohesion. Okay? Now cohesion means like coming together, and what that means for water is water sticks to itself. Okay? It beads up. I'll put those in quotes. So water beads up. Okay, now we saw that whenever, just like right here, we put the water on the wax paper, the water beaded up into little bubbles. Now that is because the wax paper that we use, just like the skin on this leaf, is non-polar. They don't want to hang out, they don't want to play together, so the water sucks up and tries to get away from that paper because the water would rather stick to itself so that it can hydrogen bond. Okay, so cohesion is caused by hydrogen bonds. Okay. We also saw this here, like with the paper clip. Okay. So because we were very gentle, we were able to sit the paper clip on top of those hydrogen bonds and it floats. Okay. Let me check my time. Okay, we're doing okay. So that's what this spider is doing here. A couple of different animals in the animal kingdom. There's a spider, there is a lizard, there is a human Jesus that can chill on top of the water like this. And it is because they are sitting just on top of all of those hydrogen bonds. We call this surface tension. Okay, so that's what's going on over here too. It's why belly flops hurt. Make surface tension. Okay, it's why belly flops hurt, is because like you are landing on top of all those hydrogen bonds and it's like getting slapped. Okay, so our first property of water is cohesion, which means water sticks to itself. Okay, now our second property of water is called adhesion. Okay, and it's kind of the opposite. It's kind of the like inverse of cohesion. Cohesion means water sticks to itself. Adhesion means water sticks to other things as long as they are polar. Okay? Because remember, water is a polar molecule. It likes to hang out with other polar things. So the non-polar stuff doesn't want to hang, but as long as it's polar, water will stick to it. Okay? And it is because of hydrogen bonds. Okay? So if, like here for example, this fly, okay, the hair on this fly has a polar charge to it, which means that the water is going to stick to the hair on this fly. And the water itself will form hydrogen bonds with the thing it's sticking to. Okay? Now, that is why we saw the water do this to the tissue paper, okay? Because the tissue has polar molecules in it, and the hydrogen bond climbed those polar molecules by making, the water climbed those polar molecules by making hydrogen bonds, excuse me. We call that capillary action, okay? Which is this right here, where water can climb things. Okay, that's why whenever it rains outside and you're wearing blue jeans, if you step in a puddle, the water, like you'll get wet all the way up to like your knees sometimes. It's not because you stepped in water up to your knees, it's because, okay, the water climbed, all right? And you can also see that in this right here, okay? So, you guys probably learned this either in middle school or in Mobley's class. This is called a meniscus, and it's a problem when you're measuring water. You have to measure to the bottom here because the water will climb up the glass. That doesn't happen when you're measuring oil, okay? And it's because the water is polar and it climbs up the sides of the glass because the glass is polar, whereas over here you have this non-polar oil and it doesn't climb up the sides of the glass. Okay? Cool. So here we have an example of both cohesion and adhesion working. All right? So we have this guy right here walking on top of the surface tension in the water caused by cohesion. The water sticks to itself. So that means that, the hydrogen bonds here are, all interconnected, and he is standing on top of those hydrogen bonds, taking advantage of that surface tension. And then over here we have adhesion, where we're doing capillary action. This water is climbing up the underneath part of this leaf, which has a polar charge just like the water. So it's climbing because water will stick to other things as long as those other things are polar. Okay. We will call it right there. Whenever we come back after the long weekend, we will talk about the final property of water, which is one that we did not do a lab about. So we'll come back. We'll talk about that. I hope you guys have a good long weekend, and I will see you later. Goodbye.